G'day, everybody. So we'll get started. We don't have much time. I'm Blair Bethwaite. I'm from Monash University. I'm a senior HPC consultant there, and I'm also the co-chair of the OpenStack Scientific Special Interest Group. And I'm presenting today with Erez from Mellanox, and he's going to take you into this now.
Hi, good afternoon, everybody. I'm Erez Cohen. Going to be very difficult to talk about machine learning and OpenStack all in 10 minutes. So we'll get going. We already lost half a minute here. Every minute counts. So for any of you that was sleeping for the last 2 years, machine learning is really everywhere. This is the next revolution that changed completely the industry. Anything you do today is behind it, there is machine learning. Machine learning is basically a different way to compute machines. Instead of telling them what to do, we teach them to learn. And by learning, they decide themselves on what to do. Machine learning is a very vast field. The revolution that we're seeing is as a result of this new subfield called deep learning or deep neural network, which is inspired by how our brain or any animal brain works, which is basically a bunch of neurons that connected together. And there is some input that goes into that neuron, and together with some weights that are applied on the connections between these neurons, there is a result that's coming out. And it sounds very simple. Actually, the elements themselves are very simple, but the implications are very substantial. And this is still on the overview. The way deep learning works is that there's two phases to building the model. The first is the training phase, which you can see on the top part. Basically, we're building a model, which is those neurons and the connections, and the weights at that step is just default random numbers. And then we are feeding that model with some training data, which is pre-classified. Basically, let's say an image that it says if it's a dog or a cat. And this image goes through the network and yields some results. And by an iterative manner, those parameters that set the model are being slowly calculated to form a model that eventually will be able to predict very reliably if the input data is a dog or a cat, just as an example. This is the training phase. The other phase, the inference, is once the model is already learned and configured, we can stream through it some data that is not classified, and the model itself will classify this data. Now, both the training and the inference have very common elements. Both of them are very CPU intensive, while the training is far more intensive. This is higher than anything that we do in normal computing. This is more close to high-performance computing, and this is why GPUs are so common in machine learning these days, because they provide the computational power to drive this computation. Another thing that is unique for that kind of workload is the network. Because we need a lot of computations, we don't get it by a single GPU or a single server. We kind of build clusters that need to work together to drive this results, and the network element is critical to drive that properly. And we'll talk about that in a few minutes. And the last point here is the storage. We'll not go into that as well because we don't have time, but the storage is really a key element in driving a lot of data in and out from the machine learning framework.
OK, so I'm just going to talk quickly about provisioning GPUs with OpenStack. Obviously, so Erez mentioned they're really, I guess, a key accelerator for deep learning. So you can do that pretty easily today. There's been actually, there was a talk earlier this morning. OVH guys were talking about on their cloud how they do GPU instances there. And actually earlier today, I also minted that wiki page, GPUs, which pulls together a bunch of information that was existing out there in the community, what works and what doesn't work. Of course, you can do ironic or PCI pass-through as well. If you're already doing a bare metal cloud and a node has a GPU in it, then you get the GPU. But PCI pass-through also works quite nicely. So that's just using Nova. We can't go into all the details here, obviously, but this sort of shows how you can just define a flavor once you've set this up. that this flavor wants 2 P100 GPUs. It also has a Mellanox virtual function as well, and then we can obviously get an OpenStack server that has those properties. That's what you can do today. What is coming upstream, and in fact there was recently an RFC proposed on OpenStack Dev for adding MDev support, which is a new feature upstream in Linux. It was landed in 4.10, and that supports vGPU. So that's for sort of essentially carving up an individual GPU into multiple virtual GPUs that can be then assigned to different virtual machines. With PCI pass-through, you can only do a one-to-one assignment or many-to-one VM, rather than multiplexing the device like you can with vGPU. There's also some important security aspects to think about with PCI pass-through as well. And if you want to go into the details of those, then I encourage you to have a look at that link as well.
Thanks, Blair. So around the network, before we go into the OpenStack and how we need to configure that, a very important element for running efficient machine learning is using RDMA. RDMA is a transport service similar to TCP or UDP, but far more advanced. It provides ability to do remote memory reads and writes to remote servers, not only send, receive, but it also provides kernel bypass to provide the low latency so application can send and receive directly from user space, and a full hardware offload. So all the networking is done by the NIC rather than have that on the CPU. In the end of the day, from the application perspective, it provides low latency, high bandwidth, and low CPU utilization. It is very common in high-performance computing, in-memory databases, but now also in machine learning. And the reason it's so popular with machine learning is because of the patterns that are required to drive machine learning, the networking patterns. So what you see here on the right-hand side, this diagram is basically how we distribute training on multiple servers. This model is called data parallelism, where every worker there between the three holds the full model, the network model of the neural network, and the data is split between the different servers. And what we do here is basically every server calculate some of the model itself, and then there is a parameter server that kind of consolidate this information, do an averaging, return it to the worker, and then this goes on in an iterative manner until the model converge. Now, this traffic that goes between the parameter server and the worker can be very bursty, can be very high bandwidth. Models may be 20, 30, 50 gig of different parameters. So there's a lot of heavy traffic around the network, and RDMA really drives a much more efficient use case. So the main framework for machine learning, like TensorFlow, Caffe, and so on, all support RDMA today. And the reason for that is basically this chart. What you see here is a comparison between, in the same system, between RDMA-based machine learning workload and TCP. And you can see, I'm not going into the details because we have basically a minute, but you can see that the RDMA-based provide about 50% more performance. Those machines are very expensive. The system here that you see is the reference architecture. You can find it on the web. Every server has 8 GPUs. 4 servers like that cost about $250,000. So doing 50% more just by using advanced networking is very significant. In terms of OpenStack, to get RDMA is actually easy. It is already available in OpenStack. What you need to do is use SRIOV, which is part of Neutron. And once you use SRIOV to export the NIC to the VM itself, you'll get RDMA if you use Mellanox NICs. With that.
Okay. So I won't say too much about this, but at Monash, we have a system which is dedicated to high-performance data processing. It was not initially built for a deep learning workload. It was initially built to take this and turn it into this. So this is cryo-electron microscopy. But the key thing is that the platform that we've got here actually lends itself very well to deep learning workloads as well. And so the Mellanox guys have stood up an OpenStack Pike lab and done a comparison of bare metal versus a pass-through, like a KVM pass-through based Nova install with Tesla K40 GPUs and Mellanox 100 gig. And you can see the side-by-side comparison here, and running these deep learning models is actually pretty much exactly on par. So it's a very good result. I think that's it. Yeah, where are we? Here we go. Oh, and so that's the end of the talk. Tomorrow, I've got another talk with NVIDIA, which probably go into some of this a little bit more, particularly on the GPU side of things, and talk about how you can run DevStack on DGX. And that's it. Thank you.
Thank you very much.